The ClearSight system is comprised of the ClearSight non-invasive finger cuff, pressure controller, heart reference sensor, and hemodynamic monitor. The system provides real-time, continuous beat-to-beat blood pressure, cardiac output, stroke volume variation, and systemic vascular resistance. Blood pressure originating from the heart and clinically measured at the brachial site is transferred through the arterial system throughout the body, until finally reaching the arteries in the fingers. The ClearSight finger cuff, along with its infrared sensing technology, measures blood pressure's variation over time and displays the resulting arterial waveform on the Edwards monitor. Blood pressure, pulse rate, and stroke volume are calculated from the arterial waveform. Cardiac output, stroke volume variation, and systemic vascular resistance are derived from these measured parameters. The ClearSight system can utilize one cuff for up to 8 hours or two finger cuffs for up to 72 hours, alternating between two fingers every 60 minutes. Each ClearSight finger cuff consists of the following components: an inflatable blood pressure bladder, an infrared light, and a receiving light sensor. The cuff wraps safely and securely around the middle phalanx of the index or middle finger. Looking at the finger and cuff in cross-section shows that the infrared light and receiving light sensor work together to continually measure the changing volume of the arteries, which pulsate at the same rhythm as the heart. The pressure controller manages how much pressure is exerted on the finger by continually adjusting the pressure in the finger cuff's inflatable bladder until the arteries and bladder are equal in pressure and the arteries no longer pulsate. The volume of the arteries at this point is referred to as the unloaded volume. The pressure that is required to continuously maintain the unloaded volume is equal to the blood pressure in the finger. This technique of measuring and maintaining the arteries at a certain volume consists of two processes: physcal and the volume clamp method. When measurements are initiated, the ClearSight system runs physcal, the real-time process which calibrates the blood pressure measurement by determining and periodically updating the target unloaded volume, known as the set point. Note that throughout this section, a red line will be used to represent physcal, and a gray line will be used to represent a traditional radial line pressure reading for comparison purposes. This will show that physcal will accurately mirror an existing arterial line output. The physcal process can be identified by its characteristic staircase-shaped waveform, which indicates the ClearSight system is stepping up and down in pressure in order to calculate the proper unloaded arterial volume. Typically, the first blood pressure waveform and its associated data will be displayed on the monitor in approximately 20 seconds. Physcal periodically recalibrates the system, which is essential for tracking the set point when smooth muscle tone changes during events such as vasoconstriction, vasodilation, and temperature change. This calibration initially begins at 10-beat intervals and increases to 70-beat intervals depending on the stability of the finger physiology. The volume clamp method is the process which uses a control loop to change the pressure in the ClearSight finger cuff in order to control the volume of the arteries and directly measure the finger cuff pressure in order to display it as a waveform on the Edwards monitor. The volume clamp method, which is located within the pressure controller, consists of the following steps. The arterial volume, which was measured by the infrared transmitter and receiving light sensor, is compared to the physcal set point. The pressure needed to counteract any arterial diameter change is determined by a controller. The controller then sends a signal to the control valve, which dynamically manages the amount of pressure applied to the finger cuff. At the same time, the transducer directly senses the cuff pressure and translates it into a point on the blood pressure waveform. This continuous control loop and adjustment of the cuff pressure is performed 1,000 times every second, resulting in a real-time finger pressure waveform. Since the arteries narrow as the distance from the heart increases, increased resistance and backwards reflection of the pressure waves occurs. This results in varying pressure levels and waveform shapes. The brachial sight has long been the clinical standard for non-invasive blood pressure measurements. The finger sight, however, has slightly lower mean pressure levels and usually an increasingly peaked waveform toward the periphery. Therefore, the finger pressure waveform must be transformed to be comparable to a brachial sight waveform. The ClearSight system does so using a mathematical transfer function based on a vast clinical database. In order to measure and display blood pressure properly, measurements must be made at heart level. The ClearSight system, however, is a finger-based monitoring system. Therefore, the EV1000 heart reference sensor, or EVHRS, is put in place to compensate for hydrostatic pressure changes due to differences in height between the finger component and the heart component. Without the EVHRS, changes in the patient's finger position relative to the heart will affect the blood pressure measurements. With the EVHRS in use and the heart component remaining at the heart level, these movements of the patient's hand are automatically compensated for and will not affect the blood pressure measurements. After the arterial waveform has been reconstructed and recorded as a comparable brachial arterial waveform, a physiological model of circulation called the ClearSight system pulse contour method is used to non-invasively and continuously calculate beat-to-beat stroke volume and cardiac output. When pumping blood through the body, the left side of the heart experiences an impedance referred to as afterload, shown here as Zn. This impedance is experienced due to the relationship between blood pressure and blood flow, which in this case is equivalent to stroke volume. By rearranging this relationship and individualizing it for each patient, we can use blood pressure and afterload to calculate stroke volume. We can calculate blood pressure, the first component of stroke volume, by using the systolic portion of the brachial arterial waveform. We can estimate afterload, the second component of stroke volume, using a physiological model of the afterload experienced by the heart. This model is individualized for each patient using the patient's age, gender, height, and weight. Once we have calculated blood pressure and estimated afterload, we obtain a final estimate of stroke volume for each heartbeat. Cardiac output is then calculated by multiplying pulse rate by stroke volume. All other hemodynamic parameters are then calculated from the arterial waveform in combination with stroke volume and cardiac output, including blood pressure, pulse rate, stroke volume variation, and systemic vascular resistance. The ClearSight system, a non-invasive monitoring system providing beat-to-beat continuous blood pressure and other key hemodynamic parameters. Edwards Lifesciences, delivering clarity in every moment.